Thank you very much. So we're going to go back to where we stopped yesterday. The plan is to give what I really feel would be fair to say is a complete proof of the solution to the lattice point counting problem with an error estimate. And I will then explain why. Well, first I will explain. I will compare this result to those that are already known, and then we will move on to explain why the solution of the lattice point counting problem is the first fundamental step in proving the ergodic theorems that we stated a long time ago, namely on Monday morning. And we're going to indicate the proof there too, and then we're going to move back to spectral theory and representation theory and try to obtain and explain when we can obtain spectral estimates which are even better than those given by the principle of transferring from a general representation to the regular representation. Okay, so our setup, to remind you very briefly, is that G is a simple Lie group and O epsilon is a small neighborhood of the identity. We have an increasing family BT of sets in G, and it is called admissible if there exists a constant C, T naught and epsilon naught, such that for all sufficiently large T and all sufficiently small epsilon, we have two properties. The properties are sort of local stability or approximate stability. If you perturb the set BT from both sides, then you really don't change all that much. And the second property is simply uniform Lipschitz property of the log of the volume, or the measure. And the lattice point counting result that we had last time is as follows. G is a connected Lie group. Yeah, I guess simple is not necessary up there. So G is a connected Lie group. Gamma is a lattice, BT are admissible, and what we have two parts to the result. One is that if the mean ergodic theorem holds, so that the averaging operators acting on L2 G mod gamma converge to the space average, then the main term of the lattice point counting result is what you expect, namely the volume. Okay, this is one result, and the next result is more significant, is that if you actually have the effective mean ergodic theorem, namely if the convergence of the averaging operators on L2 G mod gamma to the space average has a certain rate of convergence, which is given, say, by a certain power, negative power of the volume, then in fact you have a bound for the next term in the asymptotics, namely the number of lattice points divided by the volume is 1, up to an error which is bounded by a negative power of the volume, but that power of the volume is compromised by dim G plus 1.
Amos, condition 2, in case of balls, that means polynomial growth of ball of volume?
Oh, no. For example, if the growth is e to the t, yes, then this property is satisfied. If the mgbt is e to the t. Okay, so the first step we had is that we apply the mean ergodic theorem. This is very, very simple. We take a small neighborhood of the identity and we look at the normalized characteristic function chi epsilon. We consider the gamma periodization of chi epsilon. We sum over its values, the values of its translate. And we end up with a small bounded function on G mod gamma with compact support near the coset of gamma. And it has integral 1. And if we apply the mean ergodic theorem to phi epsilon, it follows from Chebyshev's inequality that the set where the averages deviate from their limiting value by more than delta, the measure of this set converges to 0. We call this the deviation set for our purposes. So in particular, for sufficiently large t, the measure of the deviation set is smaller than the measure of this little neighborhood. And so there must exist gt in this neighborhood which is not in the deviation set for sufficiently large t. So what does it mean? So I'm going to spell out this expression now. I'm going to spell out what does it mean that this point gt is not in the deviation set. And what it means is the following claim. Given epsilon and delta positive for t sufficiently large, there is some small element gt in the neighborhood such that the average of phi epsilon over the translates in bt are between 1 plus delta and 1 minus delta. Later on, we're now going to consider this integral. So you should remember that this integral is bounded by mg, by 1 plus delta times mg, and dominates 1 minus delta times mg, bt. Okay, so now we would like to understand this expression. And the way we understand this expression is that we remember that phi is a certain sum. So we change the order of summation and integration. So by definition of the averaging operators, pi g mod gamma, well, it's the of phi epsilon, it's the average of the translates of phi epsilon. Phi epsilon is a certain sum over translates. So I change the order of summation, and I have the sum over gamma of 1 over mgbt of chi epsilon g inverse h gamma. And g ranges over bt. And what we're going to do now, we're going to have an extremely simple geometric comparison argument for these expressions. And the main point there is going to be admissibility. And so claim 2 is that these sums, this is precisely the expression that appears here. These sums have the following property. If you integrate phi epsilon over bt minus c epsilon. So you take a slightly smaller ball and you look at this integral. Then it's dominated by the number of points in gamma intersect bt, and it's bounded by the integral over a slightly smaller ball. So here we have bt, the parameter is t, gamma intersect bt, and here we have a ball, let's say, of a slightly smaller radius, and here a ball of a slightly larger radius. And this follows from the following argument. So by definition, this integral is a certain sum. Okay? So phi epsilon is this sum, so this integral is a certain sum. Now, in the sum, in this integral, of course, we're only interested in integrands which are non-zero, right? And suppose that you know that this integral is 0 unless gamma is in gamma t. Supposing that you know that in this infinite sum, you really do not need to take any gammas which are outside gamma t, because this integrand is 0. In that case, you can dominate this sum by summing over gamma t, and you can take the integral over g, which certainly makes things larger, but the integral over g is 1, and so you get the number of points in gamma t. So what we need to show is that this integrand is 0 unless gamma is in gamma t. And that follows immediately from admissibility, because if chi epsilon g inverse h gamma is non-zero, where g is in bt minus c epsilon and h is in o epsilon, this is the situation we're in, if you look here, well, then clearly g inverse h gamma must be in the support of this little function. And the support of this little function is o epsilon. And if you change, what's the word? If you do the multiplication, then you see that gamma is in h inverse bt minus epsilon times the support. This is contained in O epsilon bt minus C epsilon O epsilon, so it's contained in bt by admissibility. So that in this sum, we don't have to take anything outside gamma t, so that's how we get this estimate. Okay, now the upper bound is very similar. So, of course, it's clear that chi epsilon is non-negative and it has integral 1. So now we want to consider the integral over a slightly larger ball of our function phi epsilon. And it's clear that we can take a sub-sum. Remember that phi epsilon is the sum over all of gamma. So we can certainly take the sum over a subset of gamma. And now suppose that this integral is in fact 1. Okay, so if this integral is in fact 1, then what we have here is the number of points in gamma t. So now we have to show that the support of this function, is contained in bt plus c epsilon. And the reason why this is true, we can use this inequality provided that for gamma in gamma t, and for h in this small neighborhood, the support of this function, g goes to chi epsilon g inverse h gamma, which is h gamma times the support of chi epsilon inverse, is contained in bt plus c epsilon. In that case, our integral over the little characteristic function is 1. So we pick up at least all the points in gamma t. And once again, this is true by admissibility. So now taking t sufficiently large and take h to be gt, the point that we were able to find inside the small deviation set, and using claims 1 and 2, we conclude that gamma t is less than or equal than 1 plus delta m bt plus 1 because of the fact that gt has small deviation. And by admissibility, this is bounded by 1 plus delta 1 plus c epsilon mbt. So if you divide by mbt, you see that you have an inequality. And so this proves the upper estimate and then the lower estimate, and the first part of the result is done. If you have a mean ergodic theorem, which as far as we're concerned means you can use Chebyshev's inequality, then you get the main term in the lattice point counting problem. Now, counting with an error estimate is really just the tiniest little variation of this argument. All you have to do is the following. we now assume that we have a rate, the averages of pi beta TF converge to the space average at this rate, and we must show that we have this error estimate. And so first, let's go back to this little neighborhood that we have, and we took a Lie group of dimension n. So certainly the measure of a small neighborhood of the identity is epsilon, is well, given by epsilon to the n for small epsilon. And therefore, the L2 norm of the little bump function is epsilon. The bump function, I remind you, was normalized. So it's given by epsilon to the minus n, where n equals dim g. Now, the mean ergodic theorem and Chebyshev's inequality, in this case, obviously gives a much stronger result. Namely, that the same set of deviation that we had, large deviation that we had before, is bounded by delta to the minus 2, epsilon to the minus n, and the measure of bt to minus 2 theta. I'm using the Chebyshev inequality in L2. And so here, the measure of the set of deviation decreases in t with a prescribed rate determined by the effective ergodic theorem. That's the new ingredient. And as we saw above, points x in the complement of the deviation set give us an approximation to our counting problem with quality delta, if you recall. And we must also require that the measure of the deviation set be smaller than mg o epsilon. Okay, in order to ensure that we have good points, namely small deviation points in O epsilon. So now I want to make an important point, which is that the estimate of the measure of the deviation set holds for all parameters t, epsilon, and delta. All parameters t, epsilon, and delta. Since the mean ergodic theorem with an error term is a statement about the rate of convergence in operator norm, and therefore it's uniform over all functions, it's not going to come as a surprise that a uniform norm estimate, namely an operator norm estimate, is a very powerful tool, and that's one case where one uses it. It applies equally well to all bump functions phi epsilon. It's a statement about all functions in the Hilbert space and all parameters t. Okay, well, I mean, that's just the estimate. And for all delta, because Chebyshev's inequality is true. And so the upper error estimate in the counting problem is, as before, the same estimate. Gamma t is less than or equal than 1 plus delta, 1 plus c epsilon, the measure of bt. And if we take delta to be epsilon to be m of bt to the minus theta over n plus 1, then this choice balances the two significant parts of the error estimate and meets the condition above, namely this condition. And so if you put this in, if you put these values in, then you get that the error estimate is precisely what we have here. And you can now see that the appearance of n plus 1 or dim g plus 1 has to do with the dimension of the Lie group. And really the way it comes about, and that's a very fundamental issue here, and it was mentioned yesterday, The issue is that, you know, lattice points is just a countable set of discretely embedded points, and they are totally unseen by any Lebesgue argument. What you have to do to observe the lattice point is really put a little bump function near each one of them. Then you have a function in L2, and you can apply various operators to it. Eventually, you want to take epsilon to 0, but this smoothing operator is going to cost you, a smoothing operator of taking O epsilon to 0 is going to cost you din G plus 1. And that's a very, I would say, very wide-ranging principle. It's very difficult to go beyond that. Yes? Let's see if we can make this comparison. Yes. Yes. Now, in this argument, I don't think so, because actually the way this thing works, I'm not sure I want to get into this whole discussion, but just to answer your question, the way these things work is that, for example, in SLN, you see, what's going to happen is that the LP that you need, P is higher and higher as a function of n. It's maybe 2n or something. And that means that you have to take a larger and larger tensor power. And because of that, you're going to be compromising your error estimate as n goes to infinity. So, yeah. Okay, now another point I would like to make is that in the ergodic theoretic approach that we have taken, the important feature of uniformity of counting lattice points in finite index subgroups, lambda, is immediately apparent. As you can see, gamma played a very small role here. And really, all that is needed is that the averaging operators pi beta t satisfy the same norm decay in the space L2 G mod gamma. So we have, sorry? Thank you, G mod gamma. No, G mod lambda. I'm now ranging lambda over finite index subgroups. Okay. L2 G mod lambda. Once you have that, you have a certain rate in Chebyshev's inequality, and gamma is completely outside the picture. And this holds when the set of finite index subgroups satisfy property tau, namely when the spectral gap appearing in these representations has a positive lower bound. If you like, this is a definition of property tau. And property tau has been shown to hold for the set of congruent subgroups of any arithmetic lattice in semi-simple Lie group. This is a very long story. Well, okay, the word Selberg, of course, appears here, but actually Selberg is, I think he's the first to establish an instance of property tau in the case of congruent subgroups of SL2Z, and since then it's been a very long story, but it's been established in complete generality. But you can see that there is nothing more to be said. Property tau is a further spectral ingredient, which tells you that, in fact, for all of these groups, lambda, pi beta t has the same uniform bound in L2 G mod lambda. So you plug that in and you get this conclusion. There is really nothing more to say. But this property is really quite useful. I'm not sure we'll be able to see examples of that, but okay. So let me mention some previous results. So the classical non-Euclidean counting problem asks for the number of lattice points in a Riemannian ball in hyperbolic space HD. For this specific case, the best known bound is still the one due to Selberg already in the 1940s, or to Lax-Phillips in 1970s. And more recently, Bruggemann, Grunwald, and Miatello have established similar quality results for lattice points in Riemannian balls in products of SL2R. This is the best result in the first case for SON1, and in the second case for products of SL2s. But the real rank 1 case, or even I would say hyperbolic case, plays a very significant role in this. Riemannian and other biK-invariant balls in certain higher rank simple Lie groups were considered by Duke, Rudnick, and Sarnak in 1991. And in this case, they have obtained the best error estimate to date. And this error estimate is matched by theorem E that we've discussed, except that when you have biK-invariant averages, you have to adjust the argument to this case, and then you can match this error estimate. So basically, what we've been going through, and I'd like to emphasize this point, I think it's a very simple argument, and I really think it's fair to say that you've seen it all. It's really quite straightforward, but it gives the best result that is now known for simple algebraic groups. So that means really that the lattice point counting problem in higher rank groups really has a long way to go. It's difficult to make progress on it, and that is the reason why, the complexity of the spectral theory here is the reason why the only success that this has seen is in the case of SL2 and products of SL2, essentially. Okay. Now, Eskin-McMullen in 1991 devised the mixing method, which applies to general well-rounded sets, but have not produced an error estimate. Mocourant in 2005 has obtained an error estimate using an effective form of the mixing method, and so have Benoit and O in the S-algebraic case. But the resulting estimates are weaker than those of theorem E. And the reason for this is very simple to explain, because the spectral estimate that we have for the averaging operator on a ball, this spectral estimate is necessarily better than just a statement about mixing. It's essentially, if you like, the reason why the L2 norm on a probability space, let's say, of a function is less than or equal than, well, it's usually strictly less than the L infinity norm. What mixing does in this context is that it looks at the point of smallest distance where you have, so it's essentially an estimate by the smallest decay you have in BT, and packaging things in, for the whole ball is necessarily a better estimate. And that what turns out in the exponents that they have obtained. Now, I'd like to pass to another point. I'm going to be very brief about it, but I think it's worth mentioning. So everything we've done here, the fact that it was a connected Lie group was really just to make things a little bit more friendly, but there is nothing intrinsic in it. It was very basic arguments about admissibility, which you can define, geometric comparison arguments by group multiplication, which you can define, spectral estimates of operators. So I'd like to emphasize this point because this argument is true essentially for all locally compact groups. If you have these ingredients, and you certainly have these ingredients for a wide variety of cases outside connected Lie groups. And so, for example, it was a very it was and it is a very interesting problem to count rational points. So one considered the set of, not the set of integer points this time, but the set of rational points. And one can try to count them, count rational points of bounded height, or if you like, rational points of bounded denominator on algebraic varieties homogeneous under a simple algebraic group defined over Q. And in particular, this was considered for the group variety. Group variety is the most basic case, perhaps. This has been considered by Shalaika, Taklubigash, and Chinkel in the 2000s and by many other people. And they used very complicated approach, which is a direct spectral expansion of the corresponding, what they call the height zeta function in the automorphic representation L2 G mod gamma. And in particular, they use what is known as regularization estimates for Eisenstein series. I'm not going to try to explain any of these terms, but I just want to impress you that this is a very complicated approach. And Gorodnik, Mokoran, and O have used the Eskin-McMullen mixing method in this problem, and they have obtained a count for rational points. Maybe I should mention that the problem itself is related to a famous conjecture in arithmetic geometry called Manin's conjecture. But actually, it's possible to consider the group that we have. We have a certain simple algebraic group G. And it's possible to consider it over the ring of rational Adels. And in that case, the group of rational points, the group of rational matrices, is embedded as a lattice in the locally compact group of Adels. A lattice in a locally compact group. And now one has to generalize the operator norm estimates from GF for all fields completions F to the group of Adels. And then it is possible to use the method that we presented based on the effective mean ergodic theorem here too. And the error estimate in theorem E is better than the error estimate that these methods provide. But really, to prove this result, we don't need to do much. We have to define admissibility, but this is really quite standard. There is some comments that one has to make about the spectral theory here, but the method that we presented would work essentially without change. It's true. You have to prove the Kunzi-Stein, a version of the Kunzi-Stein phenomenon for the Adel group. That's true. Yes, we had to do that. There's some surprises there, but that's okay. That's buried in the spectral theory. I would say the counting lattice point. Once you have the spectral estimate, counting lattice points is exactly the same. Okay, so now I'm going to be very brief about ergodic theorems for lattice subgroups. So if you remember, we presented ergodic theorems for gamma actions on Monday morning, and we had a mean ergodic theorem, effective mean ergodic theorem, and also an effective pointwise ergodic theorem. And I want to take 5 minutes to briefly indicate how one would approach these results. So to prove the mean and pointwise ergodic theorems for lattice subgroups, we generalize the solution of the lattice point counting problem. The lattice point counting problem, in some sense, is the most primitive ergodic theorem. Its solution is based on the most primitive ergodic action of the lattice. What do I mean by that? In the lattice point counting problem, we have considered the action of G on G mod gamma. Namely, we have considered the action of G, the action induced to G from the trivial gamma action on a point. Okay, that's not a big revelation. G mod gamma is the space, the action induced to G from the trivial action. But now what we want to do is analyze the action induced to G from a general ergodic action of gamma on some space x mu, not the action on a point. But this is an important statement because that's the philosophy of this approach. And I will remind you very briefly what is the induced action. So let's denote by y the space G mod gamma times x, or really G times x modulo the gamma orbits, as I will immediately explain. And we take it with the measure mg mod gamma times mu, where mu is the invariant measure for the gamma action. This is the action of G induced, the action of G induced from the gamma action on X. Now, what is the action here? The space is defined, the space Y is defined as the space of gamma orbits in G times X. So G times X is a nice product space, and gamma acts on both sides. And we consider the action of gamma by shifting age in G on the right and acting on X as it does by the inverse. And so gamma acts on G times X, and we have a certain space of gamma orbits. And this is called the space induced by the gamma action on X. Now, G also acts on the product via G times Hx is GHx. And it's absolutely clear that this action commutes with the gamma action and is therefore well defined on the space of orbits modulo the gamma action. And this space, it's measured theoretically isomorphic to the space G mod gamma times X, and this measure mg mod gamma times mu is G invariant. This is one of the most basic constructions in ergodic theory, and it's been used extensively for many, many different purposes. The gist of it is that if you have a probability measure preserving of action of a lattice, you are able to produce a probability measure preserving action of G. That's very good for us because we really have nothing to say about the abstract spectral theory of the lattice. The lattice is a non-amenable, countable group, and the spectral theory is completely inaccessible. On the other hand, we've just said a number of things about G actions. So the goal, therefore, is to use everything we know about the G actions, and we're going to have certain convergence theorems of certain averages, etc. But we will eventually have to work our way down, and from these convergence theorems for beta T on G, we are going to have to say something about averages on the finite set of points gamma intersect BT when it acts on X. So how do we do this? Now, the basic idea for doing this is really very, very simple, and it's motivated completely by the lattice point counting problem. The essence of the matter is obviously to estimate the ergodic averages on gamma which are given in this form. We are interested in gamma intersect BT, and we translate these functions. And that's the usual ergodic average for these sets, which we call pi x lambda t phi x. Now, we would like to estimate these ergodic averages on gamma in the right space above and below by ergodic averages of the form pi y beta t plus minus c of f epsilon y, namely by the usual ergodic averages over G, where we have taken our family T, but we allow ourselves some freedom in the parameter. And the link that we're going to have between these two expressions, the discrete average on gamma and the continuous average on G, is given, the link between these two expressions is given by setting y is the gamma orbit of a certain point Hx, and we define functions f epsilon on the induced space as the sum of chi epsilon h gamma, where chi epsilon is, as usual, a normalized bump function, and this, and then we weigh this translate by the value of phi at gamma inverse x. Now, if we had the trivial action on a point, then this is precisely what we did before. We took a little bump function chi epsilon and we periodized it over gamma. Oh, I'm sorry, over gamma. Now we periodize with these weights. We periodize with these weights. So it's a direct generalization of what we did before. We look at the translates of the bump functions and we periodize with these weights. And so we assume phi is non-negative, and now the ergodic averages pi y beta t plus minus c f epsilon, they can be rewritten in full as the following expression, where again I put the sum in the back. Now you see, we are actually very familiar with this expression already. This is precisely the expression that we had before. And we understand that it has these very simple geometric comparison arguments. And now we would like the expression in parentheses to be equal to 1, let's say, when gamma is in B t plus c. And we would like it to be equal to 0 when gamma is outside bt plus c. And this, if that is the case, we will be able to compare it to the average over the lattice points in gamma intersect B. So the weighted average we're interested in, it needs to be estimated by these geometric comparison argument. So for example, okay, so a favorable lower bound arises if chi epsilon G inverse H gamma is non-zero, and G in BT minus C implies that gamma is in BT, exactly as we had before. And a favorable upper bound arises if gamma is in gamma intersect BT, if for gamma in gamma intersect BT, the support of this function is contained in BT plus C. Okay, so this will give us a favorable estimate of this average. And now, this favorable lower and upper estimates depend only on the regularity properties of the set BT, and specifically on the stability property under perturbations by element H in a fixed neighborhood and the volume regularity, MGBT. So these properties are absolutely crucial in our analysis, and we are not able to deal with general sets in gamma. We have to have very special sets, and they have to have these nice geometric properties or stability properties, but once they do, then we can approximate these averages on gamma. So, for example, if we take some fixed O epsilon and some fixed constant C, the usual strong maximal inequality for averaging over lambda t follows from the ordinary strong maximal inequality for averaging over beta t. So it follows that for lattice actions, as for actions of the group G, the maximal inequality holds in great generality and requires only a coarse form of admissibility. Those of you who are familiar with ergodic theorems know that, and pointwise convergence, know that a maximal inequality is an absolute must, and you will never be able to make a lot of progress without it. In our case, the maximal inequality actually follows very easily from the maximal inequality for G. The mean ergodic theorem for the discrete averages lambda t requires considerably sharper argument. This is where a lot of the difficulty lies. And in particular, it requires passing to epsilon goes to 0, namely to mg O epsilon going to 0. This is a considerably more technical argument. And the effective uniform volume estimate, which appears in the definition of admissibility, is then utilized and is matched against the unavoidable quantity. This is a very bad quantity which goes to infinity as epsilon goes to 0. It's going to appear and it's unavoidable, and we have to have something to counterbalance it. And so that's where the technical difficulties lie. And the effective mean ergodic theorem requires, in addition, an effective estimate on the decay of the operator norm, and which, of course, plays an indispensable role. And this decay operator norm decay estimate allows a quantitative approximation argument to proceed. And again, using crucially the fact that the averages are admissible, and actually several further approximation and interpolation arguments. And as a byproduct of the proof, we obtain an effective decay estimate on the norms of these discrete, finitely supported operators. Okay. Okay, so I have another 10 minutes.
Sure.
Okay, good.
10 and a half.
10 and a half. Okay, so yeah, so maybe just okay, maybe I'll skip pointwise convergence. Some of you may be worried that I have to go back to proving something about a general function on X. But of course, in the induced space is a fiber bundle over G mod gamma with fibers isomorphic to X. So I'm going to have to be able to identify such a fiber and look at functions on that fiber. In Lebesgue space, this is a problem. And this requires a certain invariance principle that you have to prove. And the invariance principle allows you to pass to arguing on a single fiber, essentially. Okay, but maybe I'm going to skip this because maybe it's not so relevant to representation theory. Okay, so I also put down a few examples which I think would make a lot of sense since we discussed ergodic theorems for so long. But actually, I'm going to skip these examples, and I'm going to now turn to back to spectral theory and discuss a very important feature of it, which will play a very large role tomorrow. So we're going to skip these examples and proceed to spectral estimates which are actually better than spectral transfer. Okay, so let G, as usual, be a locally compact unimodular group with Haar measure and BT some bounded sets. G is a strongly continuous unitary representation, and we consider the averaging operators as usual. The spectral transfer estimate says that if G is a simple algebraic group and pi representation with a spectral gap and without invariant finite dimensional subspaces, then for the even integer n, which is ne pi, we have that the norm of pi beta is less than or equal than the norm of the convolution norm to a certain root, to 1 over n. Pi is tempered if pi is weakly contained in the regular, and then pi beta is less than or equal than the convolution, the norm of pi beta is less than or equal than the norm of the convolution operator for all absolutely continuous probability measures beta, and that is therefore the best possible estimate. There's no roots anymore. So tempered representations have the best possible spectral estimate. And it's a very remarkable feature of the unitary representation theory of simple groups that the best possible spectral estimate can be realized very often. I mean, this is a truly remarkable fact. Because you might think that it's very rare and it's very hard to realize, but actually it's very common. And in fact, this was observed already by Kazhdan in 1967. And in fact, it served as the cornerstone of his proof of property T. So I'm saying something that is really very, very well known. But I want to emphasize it because I think it's underutilized. And so let's recall that Kazhdan considered the group H, which is the semi-direct product of SL2R with R2. And he viewed it as a group of SL3, as a subgroup of SL3. And he considers the restriction of a general unitary representation pi of G without invariant unit vectors to H. That was the beginning of his proof. And then Kazhdan proceeds to say that pi, the restriction of pi to H has no pi R2 invariant unit vectors. So this subgroup R2, if you restrict the representation of SL3 to it, it's not going to have invariant unit vectors. And the reason for that is that matrix coefficients of pi decay to 0 at infinity. And then by Mackey's theory of unitary representations of semi-direct products, the restriction of pi to H is induced from a unitary representation of an amenable subgroup of H, as Kazhdan points out. And it then follows, because this restriction is induced from a unitary representation of an amenable subgroup, it follows that pi restricted to H is weakly contained in the regular representation of H. But we have just seen in the previous 1 minute ago that you can't do any better than that. So already in Kazhdan's original proof, in some sense you could say, well, he proved, property T has a lot of other consequences, but in the proof it was also shown that the restriction of a representation without invariant vectors of SL3 to SL2 in the upper left-hand corner is tempered. Okay, so that's what was shown in the proof. And so, in particular, in any ergodic action of G equals SL3 on a space X...
Was not H another group of previous H?
Sorry?
Was not H another group?
Ah, yes, yes, I'm sorry, because, yes, I'm sorry.
To H previous or to H this
I'm sorry. Yes. Okay, let's... okay. Well, I'm interested in SL2 and not in the semi-direct product, but okay, I'm sorry. The notation is... okay, everything that's written here is correct. The only problem is that I should call this group, call it, I don't know, L. So the restriction of any unitary representation G of SL3R to SL2 is tempered for SL2. And in particular, in any ergodic action of SL3 on a space X, averages beta T, which are supported in SL2, satisfy the best possible spectral estimates. And for us, this is a very useful fact. So, for example, if gamma is a lattice subgroup of SL3, the ergodic action of SL2 on the probability space SL3R mod gamma has the fastest possible rate of convergence to the space average. So already in the original argument regarding property T, the original argument is really, you can even say, based on the fact that subgroups of SL3 are in fact always tempered in representations of SL3. But temperedness for us means the best possible spectral estimate. So it's therefore natural to define the following for general G and non-amenable H. First we defined GH pi is tempered if the restriction of pi to H is a tempered representation of H. And then we define H to be a tempered subgroup of G if every unitary representation pi of G without invariant unit vectors has a tempered restriction to H. If you were to define this in the abstract, it would seem like an absurd definition, because how could you possibly make that happen? But actually, for example, SL2 is a tempered subgroup of SL3. And it's a remarkable fact that this is actually very common. It's not some accident of semi-simple theory. Do I have another 2 minutes? 1 minute. 1 minute. Okay. And there are several robust... Sorry? Okay. Yes, yes. So there are several robust and easily verifiable general principles which can be used to establish subgroup temperedness. The first is Kazhdan's original semi-direct product argument. This can be generalized, okay.
SL2 or SLD?
No, SL2. You have to have amenable stability groups, and this will never happen otherwise. SL2, but nevertheless, this is useful. I mean, for example, okay.
How it acts on the art of the probability?
Yeah, well, it acts suitably. Meaning it has no non-zero invariant vectors. Okay. So Kazhdan's argument can be, I don't know, generalized a little bit, and it has been over the years. It's actually a subject that received a lot of attention. Now, when G, okay, but okay, I have another talk, so maybe I'm going to start with that tomorrow morning, and I'm going to finish with the statement, or not with a statement. I'm going to present tomorrow a number of principles on how to establish subgroup temperedness, but I really would like to raise this as, in my opinion, an extremely interesting problem with a lot of interesting conclusions. I think that it would be very nice to have a systematic discussion of the condition H is tempered in G. I think this is a very deep problem in representation theory. There are several different avenues to get to that conclusion, but it's very chaotic, it's not so clear. what are the range of these methods, but I think this is a very fundamental problem. And it has, it would be very nice to understand it more abstractly or heuristically and have more examples too. Okay, thank you very much for your attention.